A smart contract on Ethereum is a program that runs on the blockchain. Sometimes this program receives a message or a call it does not immediately recognize. This is where the fallback function becomes very important. Think of it as a default handler. If a person calls a contract with a function name that doesn't exist, the fallback function is executed. It also runs if someone sends Ether directly to the contract without specifying any function to call, or if there's no data sent with the transaction. This ensures the contract has a way to respond to unexpected or simple Ether transfers, preventing them from failing silently. It is a safety net for interactions. For a fallback function to operate, certain conditions apply, especially concerning data and payments. A fallback function can be designed to accept data sent with the transaction. This allows for more complex interactions even when no specific function signature is matched. More critically, if the contract is intended to receive Ether through such calls, its fallback function must be explicitly marked as. Without the keyword, any attempt to send Ether to the fallback function will be rejected, causing the transaction to fail. There's also a gas consideration. Simple Ether transfers to a contract triggering the fallback or function are given a small fixed amount of gas, around 2,300 gas. This is enough for basic operations like logging an event, but not for complex computations. If more complex logic is needed, the sender must provide more gas. Ether, or ETH, is the lifeblood of the Ethereum network. It is not just a digital currency. It is also the fuel for all operations known as gas. Every computation, every transaction, every storage operation on Ethereum requires a certain amount of gas. This gas has a price denominated in Gwei, which is a small fraction of an Ether. The actual cost of a transaction for a user in terms of dollars or euros directly depends on two things: the amount of gas needed and the current market price of Ether. When Ether's price is high, even transactions that use a small amount of gas can become expensive in real-world terms. Users must therefore carefully consider the gas price they're willing to pay and the gas limit they set for their transactions. When you send a transaction on Ethereum, it does not complete instantly. It first enters a pending state waiting for miners or validators in proof of stake to include it in a block. Once included and confirmed, the transaction becomes successful. However, things can go wrong, leading to a failed status. One very common error message users encounter is out of gas. This simply means that the gas limit set for the transaction was too low. The operations the contract needed to perform required more computational steps than the provided gas could cover, so the transaction was halted. Another frequent error is reverted, or sometimes shown as commitment rolled back. This means the transaction was processed but failed during execution due to a condition within the smart contract code, such as an unmet requirement or an explicit call. When a transaction is reverted, any changes it tried to make to the contract state are undone, as if the transaction never ran, but the gas fees are still consumed. One of the core features of smart contracts on Ethereum is their immutability. Once deployed, their code cannot be altered. This provides trust and predictability. However, software often needs updates, whether to fix bugs, add new features, or respond to security vulnerabilities. This is where proxy contracts offer an elegant solution. A proxy contract is a relatively simple contract that users interact with directly. Its main job is not to contain the core logic itself, but to delegate or forward all incoming calls to another contract known as the implementation contract. This implementation contract holds all the business logic. The clever part is that the address of this implementation contract stored within the proxy can be changed. For such a system to be trustworthy, transparency is essential. Users and developers need to be able to easily verify which implementation contract the proxy is currently using. Standards like EIP 1967 define specific storage slots within the proxy, where the address of the implementation contract and the admin address is stored. This makes it straightforward to query. The ability to upgrade is managed by a designated proxy admin. This admin is typically an address, either an externally owned account or another smart contract like a multi-signature wallet or a DAO that possesses the exclusive permission to instruct the proxy contract to switch to a new implementation contract. This separation of concerns allows for controlled and secure upgrades to the underlying logic of a decentralized application without changing the contract address that users and other contracts interact with. When a proxy contract forwards a call to an implementation contract, it uses a special Ethereum feature called. The significance of is that the code of the implementation contract executes in the context of the proxy contract storage. This means all data is read from and written to the proxy's storage, not the implementations. This is powerful because it allows the state to persist across upgrades. However, it also means that the storage layout, how variables are ordered and stored, must be carefully managed. If a new implementation contract expects variables in different storage slots or uses existing slots for different data types, it can lead to data corruption. The proxy admin address, which controls these upgrades, is itself stored in the proxy. Its security and how it's managed, for example, immutable or owned by a DIO, are critical design choices. While proxies provide invaluable upgradability, they are not without their challenges. Aside from storage layout compatibility, developers must also be cautious about function selector clashes. This can happen if the proxy contract itself has administrative functions like changing the admin or upgrading the implementation that happen to have the same function signature as a new function introduced in an upgraded implementation contract. This could lead to unintended behavior. Despite these complexities, fallback functions and proxy contracts are fundamental tools in the Ethereum Developers Toolkit. Fallback functions ensure that contracts can gracefully handle any type of call or ether transfer. Proxy contracts, on the other hand, provide the much-needed flexibility to maintain and improve decentralized applications over time, striking a balance between the blockchain's inherent immutability and the practical needs of software evolution. They empower developers to build more robust and future-proof systems.